Well, hi there, sports fans, and welcome to another exciting episode of Physics 12. And today we're looking at lesson 4.3, and we're going to look at static equilibrium in a little bit more detail today. So static equilibrium, what that means is that an object is not moving, and this is what we refer to as translational equilibrium. So it's just not moving anywhere, it's in translational equilibrium. And the other aspect to static equilibrium is that it has to be not spinning, which we refer to as rotational equilibrium. So it's not moving and it's not spinning, it's in static equilibrium. So it has translational equilibrium and it has rotational equilibrium. They have to have both in order for it to be considered in static equilibrium. So translational equilibrium then, what that means is balanced forces. So if you have translational equilibrium, that means that your forces on the object are balanced. If you have rotational equilibrium, what that means then is that the torques around that object are balanced. So we have balanced forces and we have balanced torques. So I'm going to go completely through a couple of examples here with you, which will hopefully demonstrate how we deal with these kinds of problems. And so this is the first one that we're going to look at. This is sort of known as the chandelier type of problem. And so what we need to do is find force A and force B. And you can see that obviously force A is not along one of the axes. So again, we'll have to deal with components with that. But we have the angle there, so that's not really a big deal. We have the mass of the chandelier, and so this is a relatively easy exercise, really. And what we're doing with this one here is, again, it's in static equilibrium. And I'm going to redraw this one here because I didn't really like the type of drawing that they had there. So I'm going to redraw it and show you how I would draw this kind of thing with a free body diagram. So first of all, I wouldn't use force or the uppercase F for these because these are indeed tensions, and so I would use the uppercase T to represent tensions. This would be the weight of the chandelier, that force. So they've given us the mass of the chandelier is 200 kilograms, and so that translates into a force of 1,960 newtons. Right, so 200 kilograms means a force mg then would be 1,960 kilograms. They also give us the angle. They tell us that the angle is 60 degrees, so I put that on there as well so that we know where the angle is. And of course we have components on T1. So T1x would be here and T1y would be here. So I like to use that kind of notation because it really makes sense to me. So here's our free body diagram. This is now complete. We have everything on there that we need because there's no motion, there's no acceleration, so we don't need that on there. And so this is just simply balanced forces. So that's all we need to do. We need to write balanced force equations in the x and in the y directions, and then that will solve the problem. So our diagram is complete the way it is right here. So T1x, this component of T1, has to equal T2. Those are the only two forces in the y direction, so they have to equal each other. So we know that T1x is going to be T1 cos 60 degrees. That angle is 60, so it'll be T1 cos 60 has to equal T2. And so then we can quickly calculate what T1 is. Oh, sorry, no. We'll leave that one for now. We have two unknowns there, don't we? So we can't take that one any further. My apologies. So we're going to look now in the y direction. So in the y direction, we have this component of T1, which is T1y, and we have mg of the chandelier. And so those two have to equal each other. Those are the only two forces in the y direction. So we can quickly say that T1 sine 60 has to equal 1,960 newtons. And so we just solve for T1, so T1 has to equal 2,260 newtons. So there's T1. And now to get T2, we can go back to this one here, and it's an easy exercise then to find T2. So T2 has to equal T1 cos 60 degrees. So that would be 2,260 times cos 60, and that then equals 1,130 newtons. All right, so this is known as your chandelier kind of a problem. And this involves only balanced forces, so it's a fairly straightforward one, really. So all you have to do is make sure that you look at the forces, separate the forces in the x direction, separate them in the y direction, come up with balanced forces for both the x and y direction. And there's just a bit of a substitution here, nothing really major, and that will solve your problem for you. So the next one that we want to look at, this is like your diving board kind of a problem here. And what we need to do is find the force at A and the force at B. And this one is a little bit more complicated, and you will see that in just a minute. So again, I'm going to redraw the free body diagram. So the first two forces, or the first forces that I'm going to put on there, is we have the center of mass of the diving board, so that's going to be M1G. We have the diver down at the end here, which is going to be M2G, and the force at this point right here is going to be in the up direction. Now, it's not that obvious what direction the force in this direction is going to be. However, if you take your first step, and you pick your pivot point, which is one of your unknowns. So I'm going to pick this as my pivot point. Then you can see that the only way that these torques will be balanced around this pivot point is if F1 is in the down direction. And this seems to be a little bit counterintuitive, but we can test this. When we do get an answer for F1, if it is indeed negative, then we know that it has to be in the up direction. But we will get a positive answer for F1, which means that we have it drawn in the correct direction. And as I said, it may seem a little bit intuitive, but if you think about the situation and the way the forces are, the way the torques are, this is the only direction that F1 can go. Because if we make this our pivot point, we have torques in that direction from these masses here. The only way to counter that and to balance the torques is if this force is in that direction. All right, so we picked our pivot point. Our next step is to write our balanced torque equation. So we're going to write our balanced torques. A couple of things we haven't put on here yet. We should indicate the direction of counterclockwise and counterclockwise. Sorry, let me try that again. Indicate the direction of clockwise and the direction of counterclockwise. We should have that on our diagram. That needs to be there. And that will help you figure out your directions. The other thing we didn't put on there was the distances. And so this distance is 1 meter, and from here to here is 3 meters. And so from the center of mass then to the pivot point would also be just 1 meter. So we can write our balanced torques now. We'll assign some masses to these. So we'll make M1, which is the diving board, we'll make that 35 kilograms. And M2, which is the diver standing on the end here, we'll make her 58 kilograms. And so those are our masses. Now we can write our torque equation. So our counterclockwise torques have to equal our clockwise torques. And so the torque that's producing the counterclockwise torque, the counterclockwise torque is this one over here. F1 is producing the counterclockwise torque. If you think about it, that's the way it's producing the torque, that direction. And that has to equal the clockwise torques, which is this one plus this one. So that's what I have on the other side of the equation. Then we can put some numbers in. So M1 is 35 kilograms, M2 is 58 kilograms, and then we multiply by the distance from the pivot point. So the center of mass of the diving board is 1 meter from the pivot point, and the diver, she is 3 meters from the pivot point. So that's hence where the 1 and the 3 come from. All right, so I trust you can do the math on that, and that comes out to 2,048 newtons. Okay, so we have F1, and notice we did get a positive number here, so that's the direction that F1 is. It is in the down direction. So, and that's its magnitude there. Now what we have to do is, now we have to go with our balanced force equations. in order to find out what F2 is. So from our balanced torque equation we found F1, now we have to find F2 from our balanced forces. So how we're going to do that is F2 is the only one in the up direction, and we have 3 forces in the down direction. So that just simply means that F2 has to equal those 3 forces added together. And again, I trust you can do the math. And again, note that there's no distances in here. This is now just balanced forces, which we don't need to worry about the distance from the pivot point. That was only for the balanced torque equation. So when we're into balanced forces now, we don't worry about the distances. It's just simply the force. So we add those forces up together, and we get 2,959 newtons. I didn't write it too clearly there. 2,959 newtons is the magnitude of F2. So with static equilibrium problems, step 1 is to pick your pivot point. Usually make it one of your unknowns. And that goes a long way to helping you solve the problem. If you can pick your right pivot point, make it one of your unknown quantities, one of the unknowns that you're trying to find. And then part 2, write your balanced torque equations. That will generally give you one of your unknowns. And then you go to your balanced force equation, and that will give you your other unknown. So start with your free body diagram. Make sure you have everything on there, including the indicate which direction is clockwise and which direction is counterclockwise. And then these 3 steps here, and that's how you solve these kinds of problems.